Hi everyone, today we will be learning about how to determine if a chiral center has the R or S configuration. A chiral center is an atom bonded with 4 different substituents. The chirality of a molecule are 2 non-superimposable mirror image forms, also known as enantiomers. These 2 molecules here are enantiomers because if you were to stack them on top of each other, they would not match. Just as if you were to stack your right hand on top of your left hand with both palms facing downwards. But they are mirror image forms of each other, just as your 2 hands were if you were to face your palms towards each other. Different enantiomers will have different reactivity. The R enantiomer has a clockwise configuration and the S enantiomer has a counterclockwise configuration. An example of different enantiomers having different reactivity is that the S enantiomer of ibuprofen has a stronger therapeutic effect. To determine whether the enantiomer is S or R, you must first order the substituents 1 to 4. Then also consider if there are any wedged or dashed bonds. The order of the substituent is based on the mass of the substituent, with the greater the mass having the higher the priority. By looking at this example here to the left, hydrogen we would automatically number with 4. Then based on this chart here, which is representative of the mass of the substituents, R1 would have the highest priority, so we would number that 1, and then 2 and 3 accordingly. This is representative of the counterclockwise orientation of substituents, which is representative of the S enantiomer. If R1 were to be attached by a wedge bond, hydrogen would be attached by a dash bond. With only wedge bonds of hydrogen, you would need to inverse the orientation. So in this case, you would not need to. So the ordering of the substituents would be the same. And it has a counterclockwise configuration. So it is the S enantiomer. If R1 were to be attached by a dash bond, hydrogen would be attached by a wedge bond, meaning that it is coming towards you. Because of this wedge bond, you would need to inverse the orientation. So the substituents would be numbered the same. But because of the wedge bond, you would inverse the orientation. So before it is representative of the S enantiomer, but because of the wedge bond, it is the R. An example problem is ibuprofen. So this is the chiral center of interest. And these 4 are the substituents. So hydrogen would automatically have the least priority. So you would number that with 4. Then you would compare the methyl group, the carboxylic acid carbon, and the carbon attached to the ring. And this methyl group carbon is attached to 3 hydrogen. This carbon is attached to an oxygen, and the carbon in the ring is attached to another carbon. So comparing hydrogen, oxygen, and carbon, hydrogen is the smallest out of carbon and oxygen. So this methyl group would be the 3rd priority. So now comparing the carbon attached to the oxygen and the carbon in the ring, carbon is smaller than oxygen. So this ring group would be the 2nd priority and the carboxylic acid would be the 1st. This hydrogen is on a wedge bond, so you would need to inverse the orientation. So although the substituent has a clockwise configuration, because of the wedge bond, you would have to inverse the orientation. So I'll just write that here. And that is why this is the S version of the ibuprofen. So this chiral center has the same ordering of the substituents. But because the hydrogen is on a dash bond, you would not need to inverse the orientation. So it has a clockwise configuration, which is representative of the R enantiomer. This example, you would compare bromine, hydrogen, chlorine, and fluorine. Hydrogen is the smallest, so you would number that 4. By looking at chlorine, fluorine, and bromine, you would look at a periodic table and see that bromine is bigger than chlorine and chlorine is bigger than fluorine. So I'll just write that here. So you would number bromine 1, chlorine 2, and fluorine 3. And because both hydrogens are actually on a dash bond, you would not need to inverse the orientation. So this molecule to the left has a counterclockwise configuration. So this is the S enantiomer. The molecule on the right has a clockwise configuration, and the hydrogen's on the dash bond, so you would not need to inverse the orientation. So it is the R enantiomer. So this example of carbone, this is the chiral center of interest. These are the 4 substituents, with hydrogen being on the dash bond and it being the lowest priority, so we number that 4. These 3 are the next substituents of interest. All these substituents are carbons. So we would then look at what the first carbon is bonded with. So they are all also bonded with another carbon. So then we would look at what the second carbon is bonded with. So here, the carbon is bonded with 2 hydrogens. This carbon is bonded with another carbon. The second carbon here is bonded with an oxygen. So oxygen is greater than carbon, which is greater than hydrogen. So this group here would be the 3rd priority. And based on here, oxygen is greater than carbon. So this group would be the greatest priority, and then this would be the 2nd greatest. So we number that 1 and that 2. Because hydrogen's on a dash bond, we would not need to inverse the orientation. So this enantiomer here has a clockwise configuration, so is representative of R. This molecule here would have the same numbering of substituents. So this would be 1, 2, 3, and 4. And because the hydrogen here is also attached by a dash bond, we would not need to inverse the orientation. So this has a clockwise configuration representative of the counterclockwise configuration representative of the S enantiomer. The final example is of glyceraldehyde, with these carbons being the chiral center of interest. These are the 4 substituents. Where the oxygen is compared to carbon. Oxygen is greater than carbon, so this alcohol group here would be the 1st priority. So next we compare the 2 carbons. This carbon is bonded with an oxygen, and this carbon is bonded with 2 hydrogens. And since oxygen is greater than hydrogen, this aldehyde group would be the 2nd priority, and the other 3rd. Because the hydrogen is bonded by a dash bond, we would not need to inverse the orientation. So this has a clockwise configuration representative of the R enantiomer. The numbering of substituents would be the same for the molecule on the right, and since the hydrogen is bonded by a wedge bond, we would need to inverse the orientation. And although the substituents is representative of a clockwise configuration, because of the wedge bond, this would be the S enantiomer. Thank you for watching this video, and additional practice problems including the examples done in this video and along with the answer key will be linked in the description below. Thank you, and I'll see you next time.